Hello and welcome to Chapter 14, Alcohols, Ethers, Aldehydes, and Ketones. So we're going to be looking at how to recognize the functional groups of alcohols, aldehydes, ketones, and ethers. We're going to name and write the formulas and be able to write reactions and preparations of these four functional groups as well. Alright, let's get started with our alcohol groups. So an alcohol is any compound with an OH bonded to a non-aromatic alkyl carbon. So it's an ROH. So this is a OH attached covalently to a organic carbon. So if I have CH3CH2OH, I got the oxygen attached to this carbon, and it'll give us ethyl alcohol. So let's look at some common alcohols that you may be familiar with. So, methanol or methyl alcohol is a wood alcohol, and it's also used as a racing fuel. So a lot of times you see those drag racers, they're racing on methanol or methyl alcohol. So meth, notice one, so CH3OH, one carbon. Ethyl alcohol is actually the alcohol that we can drink. So anything that has alcohol in it, or what we think of as alcohol, so your beer, wine, any kind of spirit, your vodka, anything, that is ethyl alcohol, or ethanol, or green alcohol. So ethyl, meaning 2 carbons in that chain with our OH. We also have our isopropyl alcohol. So this is your rubbing alcohol. So this is the alcohol that's found under their sink to help with wounds. Notice that there's an iso group. So I've got a carbon that's going to hang off of our chain to give the iso. So it's also called 2-propanol, which is what the IUPAC name will be for it. So we'll see that it's a carbon hanging off with an OH attached to it. Another alcohol that we see a lot is glycerol. Glycerol actually has 3 alcohols attached to it, 3 OHs, so 1, 2, 3 triol, propane triol, or also called glycerin. So we're going to talk all about these types of alcohols into more detail here in a little bit. So let's first talk about their structure and physical properties. So alcohols then are organic compounds containing that hydroxyl OH group attached to an alkyl group, so attached to a carbon group. Alcohols have the general form of ROH. So the R meaning, remember, any kind of carbon. So some more properties of these alcohols compared to hydrocarbons. They're going to have higher boiling points. So why? That is because of their hydrogen bonds. So this is one of our topics from Chem 101 that we do need to remember is our intermolecular forces. So our hydrogen bonds, we said, were super electronegative. So that oxygen has a slight negative charge on it, and these hydrogens have slight positive charges on it. Positive and negative are attracting, so we have a stronger attraction than just our London dispersion forces, which is just carbon and hydrogen bonds for our alkenes and alkenes, so just our hydrocarbons. So just as a side-by-side comparison, I have a methanol, so 1 carbon, 2, so these are all our alcohols, and here are all of the corresponding alkenes. So I have our ethanol, so 2 carbons with an alcohol, 78 degrees for our boiling point. Whereas ethane, negative 89 degrees Celsius. So ethane is pretty much always a gas than the temperature we have on Earth. And ethanol is mostly a liquid, but it does have a fairly low boiling point, and it's low compared to water. So it is less than water at 100 degrees Celsius, so ethanol does boil sooner than water. We'll see that that's how they actually are going to separate water and ethanol is by this boiling point right here. Its water solubility, they're pretty much miscible. Miscible meaning that it'll pretty much completely dissolve in water. Doesn't matter how much you add to it until you hit that saturation point. As we go up though, that water solubility decreases substantially. Also notice that as we increase the number of carbons, we are increasing the London dispersion forces, so the boiling points do go up as I add carbons. But what I wanted to show you just mostly was just the comparison between alcohols and alkanes. So even though the alkanes also increase as I increase the number of carbons, they're always going to be less than something with an OH group, since it has a strong intermolecular force of those hydrogen bonds. Remember, hydrogen bonds can occur with anything with an oxygen, nitrogen, or a fluorine. So anything with an NH, an OH, or an FH will be able to have a hydrogen bond and create these strong intermolecular forces, therefore having higher boiling points. Because it takes a lot more energy to break those bonds because they're so close together, they're so strong. Think about it like having two strong magnets stuck together versus like two little refrigerator magnets stuck together. So those little plastic refrigerator magnets that you get in the mail or such, those are two really easy to pull apart. But you get those really strong magnets and stick them together, much more difficult to pull apart. So that's what's happening with these bonds. The stronger the bond, the harder it is to pull apart, the higher the boiling point will be. As we saw in our last slide, alcohols with a small hydrocarbon part are water soluble. They will mix with water. Where alcohols with the large hydrocarbon parts are insoluble. So those hydrocarbons are hydrophobic, i.e. it doesn't like to be around water, where our electronegative groups do like to be with water, so our OH. So notice that when we actually look at these electron densities of the molecules, the oxygen is red. Red meaning a negatively charged part of the compound. The greens are pretty neutral parts of the compound, and the blues show a more positive part of the compound. So we've got this highly negative part, and it's a decent amount of our compound here for methanol, whereas although we still have those positive and negatives here, we still have a whole heck of a lot more surface area that is green, that is hydrophobic, that does not want to be around water. So this part right here, that would dissolve in water, but since it's got this big tail of a hydrocarbon, the overall molecule will not dissolve, since this will have a tough time interacting with water because it's got this big back to it. Alright, so let's look at some more properties of alcohols. So London dispersion forces, we said, can increase the boiling point of the alcohols as the non-polar portion of the molecule grows longer. So that's what we had said earlier, as the more carbons that we add, the higher the boiling point will be. So let's take a second and think about which of the following molecules can form hydrogen bonds to another molecule of the same type. So take a few seconds and look at these molecules, see which ones can form hydrogen bonds. Alright, so the molecules that we're looking for are ones that have an O and an H. So if we look at water, water has an OH, they're attached to each other. Yes, water will form hydrogen bonds. For our ethanol, I have an OH attached to the carbon. Yes, it'll form hydrogen bonds. For this carboxylic acid, I have an OH here, so yes, it can form hydrogen bonds. Notice I didn't say anything about this oxygen. That's what we have here is our ketone. It doesn't have any hydrogens attached to that oxygen. So it's not the carboxylic group that makes it a hydrogen bond, it's the OH. I have to have both of them to make it a hydrogen bond. So that is our solution, only A, C, and D, since we have to have an N, O, or F to form a covalently attached to a hydrogen to form a hydrogen bond. So let's look at another one. Which of the following molecules has a higher boiling point? Is it going to be a ring with an OH or a ring with a CH3? So take a couple seconds, think about which one will have a higher boiling point. Well, it's going to be the one with the hydrogen bonding, the OH. So if we have an OH, we have hydrogen bonding, higher boiling point. This will have a higher boiling point than just cyclobenzene because I do have an additional carbon. However, the OH will always be stronger since it's got stronger types of bonds. So our cyclohexanol can hydrogen bond. Alright, so a little bit more on our solubility. We said low molecular weights alcohols are going to be very soluble, so up to 5 or 6 carbons. We'll find out that this is kind of a common trend. Any kind of functional group that has a polar end to it is typically soluble to about 5 or 6 carbons long, and then it starts to become insoluble. So if I have 1, 2, 3, 4, 5, or 4 carbons here, 7 grams per 100 milliliters. So if I have our ethanol, very soluble, but notice if I put the the oxygen on the inside for our ether, it's barely soluble because the oxygen's on the inside. It's kind of surrounded by nonpolar areas. So it is not going to be as soluble as something with a very polar OH bonds at the end of their molecules. Also, by talking about ends of molecules, I can actually have fairly long chains of alcohols that are soluble as long as I've got multiple OHs. If I've got an OH on either end, this is going to be a very soluble compound. So the solubility then is going to be determined by the ratio of hydroxyl groups to carbons on the chain. So diols and triols, so compounds with 2 or 3 OH groups, are going to be more soluble than those with only single hydroxyl groups, since they'll have multiple areas around the compound that are going to be polar. Alright, so let's figure out how we're going to name these alcohols with our IUPAC naming. So the biggest key to naming an alcohol is going to be that we're going to drop the E at the end of an alkane and add an ol, so add an OL. So then we need to name where that alcohol group is, so we're going to specify the number on the chain that we see the alcohol, and then we're going to look at the parent chain and see position and number of appearances. So we will give it a slightly different name if there are multiple alcohols in our structure. So looking at 3 examples here, I have ethanol. So ethyl alcohol is the common name, ethanol is the IUPAC name. Notice there is no number out front. That is because it doesn't matter which side I put the OH on, it's going to give us the same compound. So it doesn't matter if I put a 1 out front for ethanol. However, for propanol, there are 2 different types of carbons I can put it on. I could put it on an end carbon or the middle. So I do need to specify where that alcohol is. So I put the number 1 out front since it's attached to the first carbon. I drop the E and add an OL, so it becomes 1-propanol. However, if I put that OH group on that second carbon instead, it is now 2-propanol, which is what we call isopropyl alcohol. So it's like having an isopropyl group hanging off of that alcohol. So like you said before, that is our rubbing alcohol that we're using. Notice that it is a different type of alcohol than the alcohol that we drink. So this is why a lot of teenagers thinking that they got alcohol in their cupboards get very sick, because they are different types of alcohols. So we said that we always wanted to name our special groups first as the lowest number possible. So we said our special groups were something like our oxygens or something other than carbons in our chain. So in this case, I have the alcohol, so I need to name the alcohol the smallest substituent or smallest number possible. So that means that I'm going to want to start on this side of the chain. My longest chain then is 1, 2, 3, 4, so it's a butane chain. I'm going to drop the E, add an OL to it, and then I see that it's on the second carbon. So it'll be a 2-butanol, but then we also have this methanol or a methyl group on our third carbon. So it'll then be 3-methyl 2-butanol. So even with our cycloalkanes, we are going to want to always start with that special group. So in this case, it's an OH. So we know that this has to be the first carbon, and it will always be the first carbon with the alcohol in this case. So I have it 1, 2, 3. So I have a 3-methyl and a cycloalkane, so cyclohexanol, and a methyl on the third carbon. So it becomes 3-methyl cyclohexanol. So notice we did not need to number it 1 cyclohexanol because it has to be the first carbon. There's no other position for it. We'd always number it right from that carbon. So we don't need to specify that it is a 3-methyl 1 cyclohexanol. That's the only possibility that there is. So we don't need to put it. So that is our IUPAC naming for alcohols. And as you may have noticed with some of our other examples, all of the common names are it's a common name plus the word alcohol. So ethyl alcohol or tert-butyl alcohol for this one, or isopropyl alcohol for this one. So these are the common names. You will not be tested on the common names. It will just be the IUPAC names. So speaking of it, let's give the IUPAC name for this molecule. So go ahead and take a couple minutes and write the IUPAC name for this alcohol. Alright, so for this alcohol, I need this number or this carbon to be the lowest. I find the longest chain, so 1, 2, 3. So we know it's going to be a propanol. It's on the second carbon, so it's a 2-propanol. And also on that second carbon, there's a CH3 group. So I have a 2-methyl 2-propanol. Okay, so let's look at a few more of these examples of alcohols. We talked about methanol a little bit earlier. Said that this could be our racing fuel. It is a colorless and odorless liquid. It is used a lot of times as a solvent. It is toxic and can cause blindness and death if it is ingested. So you can be thinking, why the heck would somebody want to drink this? Well, some people actually drink it without knowing it. So the reason why is because of ethanol and some of the backwoods brewing and distilling that can happen. So then they're trying to drink ethanol and people actually accidentally ingest some of the methanol that is left over. So let's talk about both of them. So ethanol, also an odorless and colorless liquid, also widely used as a solvent. This is the alcohol in alcoholic beverages. So this is the one that we want. But it's derived from the fermentation of carbohydrates. Now, when we're fermenting these carbohydrates, the sugar doesn't always completely break apart into ethanol. It does have a lot of side reactions, and methanol is also produced when you are fermenting ethanol. So when you're distilling an alcohol from grain or from anything, what happens is that you boil it in this distiller. So this is a backwoods one. Also, you could use a very nice glassware one in our labs. But the way this works is that you evaporate the liquid. The alcohol we know evaporates first. We said that the water has a boiling point of 100 degrees, but ethanol has a boiling point of 78. Well, methanol we saw has an even lower boiling point. I believe it was around 30 or so. So the methanol should come off first, and then the ethanol will come off. So typically with these distilleries is they'll start boiling their solution, and the first liquid that starts to come off is methanol. Then after all the methanol comes off, then the ethanol comes off. So if the distiller isn't careful, they may actually still collect some of the methanol and then start collecting their ethanol as well. So you'll see that a lot of times these backwoods distillers don't necessarily have the greatest eyesight because the methanol destroys your eyesight. So in the stores, and when we buy ethanol, they are regulated and they are not allowed to have any methanol in it. So if it's regulated, they know that there's no methanol. However, if you go, like I said, buy it from somebody off the street, that's not necessarily true. So you have to be very careful about who you want to get this alcohol from, and that you trust them that they took off all of the methanol first. So we said another common one was our 2-propanol. This is also colorless, but it has a slight odor, so you do kind of smell that rubbing alcohol when you know it, or when you open it. Like you said, this is toxic when ingested. Our body does not know how to break down this isopropyl alcohol, or the 2-propanol. But that is why it's a good disinfectant, antistringent, and industrial solvent, is that it kills a bunch of stuff because really nothing knows how to deal with it. So all of our hand sanitizer that we're using right now, if it has the isopropyl alcohol in it, well, it breaks apart the DNA of just about anything, or cell walls, which is why it can be used as this disinfectant and antistringent. Interesting turn of events, though, with the 2-propanol. Back, 10, 15 years ago, what you were supposed to do when you got a cut is maybe get a cotton swab, put it in the isopropyl alcohol, and dab it on your wound, and that way it kills all of the bacteria and everything that could be in the wound. However, they've actually found nowadays, they've done a bunch of studies, and they found that by doing that, yes, you are killing all of the bacteria, but you're also inhibiting your cell growth. So it's going to take you longer to heal because you use the rubbing alcohol. So they're not recommending that you use rubbing alcohol anymore on wounds. They're telling you to use, like an antiseptic cream, so like your Neosporin or Polysporin instead. So instead of cleaning your wounds with alcohol anymore, they tell you to use those antiseptic creams now. Another common alcohol that we use is 1,2-ethane-diol. So this is our ethylene glycol, which is our automobile antifreeze. So although we kind of live in an environment that we don't see very much snow, if we were to go someplace, up to the mountains, up to Big Bear or something, and have a place where it gets really cold, well, all of the fluids in our car can freeze when it gets really cold. However, if we put a little bit of antifreeze in there, it lowers the freezing point, so it doesn't actually freeze in our cars. And it also raises the boiling point. So if you go out to the desert, it also makes it so that your radiator fluid and all of your fluids don't just start to evaporate in your car when it gets too hot. Now the catch is that it has a sweet taste, but is extremely poisonous. So this is where a lot of animals will get into the antifreeze and die because of it. So a lot of dogs especially will smell the sweet taste of the antifreeze and get into the pipes of the car, or get into the bottle that you have lying around. So you have to be very careful if you get any antifreeze to keep it away from anybody and anything that can get into it. What I also wanted to point out with this is the name. So notice it's got 2 alcohol groups on it, so that's why it's very, very soluble in water. But notice I say it's a diol. So I keep the E now, and I add the word di when there are 2 alcohol groups. And then I name or number where those 2 alcohol groups are. So it's a 1,2-ethane-diol. And then with 3 of our alcohol groups, so our 1,2,3-propane triol, well, I've got a alcohol group on every single carbon. So it's a 1,2,3-propane triol. So once again, we number where those oxygens are, or where the alcohol groups are. Keep the E, add the prefix di or tri, and keep the OL. So this is a very viscous, thick, it has a sweet taste to it. This one is non-toxic, and it's highly soluble in water. So it's used a lot in cosmetics, pharmaceuticals, lubricants. We saw earlier that it was used for eye drops. So those lubricating eye drops, this is our glycerol. So if you have anything that has glycerol in it, it's 1,2,3-propane triol. And it's obtained as a byproduct of fat hydrolysis. So it's used a lot in soap making. So when you hydrolyze fat using your lye or your sodium hydroxide, you produce some of this glycerol. Now we talked about our TNT in our last class, so our trinitrotoluene. Well, another explosive that we are all familiar with is our nitroglycerin. So glycerin, well, it is a nitro. So you have to take your glycerin molecule, so here are 3 OHs. We add our fuming sulfuric acid, just like we did to our benzene rings, and we add the nitro groups to it. Just like the benzene groups, it destabilizes the molecule by adding those NO2s, creating a highly unstable molecule. So this nitroglycerin is actually what they use in dynamite. So you go, okay, who figured this out? What scientist figured out nitroglycerin in dynamite? Believe it or not, it was Alfred Nobel, the same Nobel that created the Nobel Prize. So Alfred Nobel took glycerin, took this fuming sulfuric acid, and created nitroglycerin. And he actually stabilized it using diatomaceous earth and carbonate. So diatomaceous earth is kind of a white powdery substance that you can actually buy at the store pretty easily. You put it on plants and it kills a lot of bugs because it's so sharp on a micro scale. But he found that the nitroglycerin gets absorbed into the diatomaceous earth, and it stabilizes it so it doesn't explode unless you have a fuse. So unless you have an outside source of heat or energy. Now, because he created dynamite, he was actually known as the Merchant of Death. He basically allowed people to kill other people much faster, and many more of them, with his invention. Now, this traumatized him so much that he actually created the Nobel Peace Prize to kind of reinvent himself and to show that, hey, I didn't mean to invent something that was an explosive and to have all of these bad consequences, but let's reward people that are very peaceful and are trying to promote peace around the world. Now this is expanded to, you can win the Nobel Prize in just about any type of science or literature, so it's expanded greatly since of his time. But kind of interesting that somebody that was known as the Merchant of Death is the one that created the Nobel Peace Prize. Alright, so let's look at a few more properties of our alcohols. So alcohols, depending on the number of alkyl groups attached to the carbonyl carbon, are classified as primary, secondary, or tertiary. The carbonyl carbon then is just the carbon bearing the hydroxyl group. So we are going to look at that particular carbon, whichever one has the hydroxyl group, and see how many other carbons are attached to it. So for example, our methyl alcohol here, this carbon is our carbonyl carbon, has the OH, but it doesn't have any other carbons attached. This one's unique, so it doesn't actually have a classification. However, our first degree alcohol, so this carbon, has an OH attached, and it has some other carbon attached. So for example, ethanol. I have this carbonyl carbon with the OH, and it's got one other carbon attached. So we're going to call this a first degree alcohol. So how many other carbons are attached to the carbon with the alcohol, or to the carbonyl carbon? That is going to be the degree number for the alcohol. We're going to find that when we look at the reactions of these alcohols, the degree of the alcohol is going to help us determine what type of reactions can occur. We'll find first degree alcohols react pretty readily because that alcohol doesn't have a whole lot around it. It's fairly unhindered. Second degree, I've got a few more steric hindrance, so I've got a few more carbons around it. So it's got less reactions. And third degree alcohols have a whole lot of carbons and stuff going on around it, so it kind of buries the alcohol in the molecule, so it doesn't react very much compared to first and second degree. So then our example of our second degree was our 2-propanol. So I've got 2 carbons attached to the center carbon, or the carbonyl carbon, and then our third degree carbonyl carbon will have 3 other carbons attached to it. Alright, let's look at an example. So take a couple minutes, see if you can determine what degree each of these alcohols is. Is it first, second, or third degree carbon, or third degree alcohol? So if I look at A, the carbonyl carbon in the center here has 2 other carbons attached to it. So that makes it a second degree alcohol. Whereas B, the carbon here is the one that's attached to the alcohol. So here's our carbonyl carbon. It's got 3 carbons attached, so it's going to have a third degree alcohol. C, here's our carbonyl carbon. It only has 1 other carbon attached, so it's first degree. And then for D, here's our carbonyl carbon with the OH attached. I have 2 other carbons attached to it, so it is a second degree carbonyl, or second degree alcohol. So just to kind of drive home the point and give a couple more examples, our primary alcohols are first degree alcohols. The OH is going to attach to 1 other carbon atom. So the carbon carrying the OH is attached to 1 other carbon. So our ethanol, our propanol. So that OH is hanging off of the end of the carbon chain. Whereas our second degree carbons, the carbon carrying that OH group is attached to 2 other carbons. So if I look here, I have 2 other carbons around it. So this is our isopropyl alcohol, or our second degree alcohol, or secondary alcohol. And then our tertiary alcohol, the carbon atom is carrying the OH group is attached to 3 other carbon atoms. So our tert-butyl alcohol. So that's where the tert-butyl comes from, is that it's a carbon with 3 other carbons attached to it. So we think back to chapter 12 when we were looking at the tert-butyl groups. Well, the tert-butyl group, we said, was the carbon with 3 other carbons attached, which makes our tertiary or third degree alcohols. Alright, so that's all of the classification and physical properties of alcohols. Next chapter, or next part, we're going to look at ethers and other molecules that are similar to alcohols. And then our third part of chapter 14, we are going to look at all of the reactions of these compounds. So we'll start with our ethers in part 2.